The problems in this video go with lesson 5.2, sum and difference formulas. Example 1, find the exact values. Part A, the sine of 195 degrees. All right, what we want to do is we want to use either the sum or the difference formula for sine, and we need to find this sine for 195 based on some angles in the unit circle because we already know the sines of those and the cosines, and we can find the rest of the trig functions. So the first thing I want to do is I want to break down 195 so that it's the sum of two angles from the unit circle, or the difference of two angles from the unit circle, either way. Now there's a lot of different ways you can combine angles from the unit circle, so any one combination is not going to be the correct one necessarily, because we should all arrive at the same answer as long as we have angles that add up to 195 degrees. And the one that I see here is 135 plus 60. 135 is over in quadrant 2, and 60 degrees is over in quadrant 1, and these are both on the unit circle. All right, now let's apply our sum property. The sine of 135 degrees plus 60 degrees is the same thing as the sine of 135 degrees times the cosine of 60 degrees plus the cosine of 135 degrees times the sine of 60 degrees. Now we're going to simplify this. We're going to look on the unit circle and we're going to figure out the sine of 135, the cosine of 60, the cosine of 135, and the sine of 60. All right, at 135 degrees, the sine is the square root of 2 over 2. At 60 degrees, the cosine is 1/2. At 135 degrees, the cosine is negative square root of 2 over 2. Now keep in mind, I'm getting all these numbers from the unit circle. And then the sine at 60 degrees is the square root of 3 over 2. Let's do our multiplication. The square root of 2 times 1 is the square root of 2. 2 times 2 in the denominator is 4. The square root of 2 times the square root of 3, that's going to give me the negative square root of 6. And then 2 times 2 is going to give me 4. And then if you want, you can write this as one fraction. Square root of 2 minus the square root of 6 divided by 4. And that is the sine of 195 degrees. All right, let's look at part B. Now we want to find the cosine at 5 pi over 12. Again, you need to find two angles on the unit circle that either add or subtract to give you 5 pi over 12. Now I generally like to add because most of the time it's easier to find two angles that add together and give you the angle you're looking for, but not always. One thing I do know here though is that 5 pi over 12 is located in quadrant 1, and that's because 6 pi over 12 is equal to pi over 2, and that is the actual positive y-axis there. So I'm probably looking for two quadrant 1 angles that'll add together and give me 5 pi over 12. And in this case, it turns out that pi over 4 plus pi over 6 will work. Let's apply our cosine sum formula. That means we're going to take the cosine of pi over 4, and we're going to multiply that by the cosine of pi over 6, and then we're going to change from addition to subtraction, and then we're going to look at the sine of pi over 4 times the sine of pi over 6. Okay, let's go to the unit circle and simplify this. At pi over 4, the cosine is positive square root of 2 over 2. At pi over 6, the cosine is positive square root of 3 over 2. At pi over 4, the sine is positive square root of 2 over 2. and the sign at pi over 6 is positive 1/2. Let's multiply here. The square root of 2 times the square root of 3. This is the square root of 6. On the bottom, 2 times 2 is 4. Over here, square root of 2 times the square root of 1. That's the square root of 2. And on the bottom, 2 times 2 is 4. And so our answer, if you want to write it as one fraction, is square root of 6 minus square root of 2 divided by 4. That is the cosine of 5 pi over 12. Notice how similar my answers look. All right, for the sine and the cosine, we should be expecting this because we're using these numbers from the unit circle, so our answers should look a lot alike. Example 2. Find the exact value of the expression cosine 99 times cosine 36 minus sine 99 sine 36. And I probably should have put the little degree signs on here, which I did not do. That way we're not looking at this as a radian problem. Okay, so none of these angles are actually unit circle angles here. And what I notice is that I actually have a pattern here. I have a cosine times a cosine minus a sine times a sine, and that sounds kind of familiar to me. And if I go back and look, right here, I have a cosine times a cosine minus a sine times a sine, and that is the cosine of one angle plus the other. So let's go back to our problem, and we're going to write this as the cosine of 99 plus 36. In the calculator, when I add 99 plus 36, that gives me 135. Oh, now that number is on the unit circle. The cosine at 135 degrees is negative square root of 2 over 2. Example 3. Find the exact value of the cosine of alpha plus beta, given that the sine of alpha is 5 over 13 and the cosine of beta is 5 over 6 for alpha in quadrant 2 and beta in quadrant 4. All right, let's expand this sum for just a second here. So we know that the cosine of alpha plus beta is going to be the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. Well, in my problem here, I'm given the sine of alpha, so that one I know, and I'm given the cosine of beta, so that one I know. The question is, how can I get this one and this one right here? And the answer is, we're just going to have to draw the triangles, and we'll have to find the cosine and the sine that are missing. Okay, so let's look at the alpha angle. It's in quadrant 2, so that means it's over here like this. The sine is 5 over 13, so the 5 is going to go here, the 13 is going to go here, and we need x down here along the bottom. So we have a squared plus b squared equals c squared. That means x squared plus 25 is equal to 169. And we'll subtract the 25 over here. We'll have x squared equal to 144. And then we'll square root both sides. And x is going to be equal to negative 12. I knew I wanted to take the negative square root because we're over here in quadrant 2 where the x's are negative. And now that I have that, I know that the cosine of angle alpha is equal to negative 12 divided by 13, because remember it's x divided by r. All right, now let's look at angle beta. Angle beta down here in quadrant 4. And we know that the cosine is 5 over 6. So our 5 is going to go here, 6 along the hypotenuse, and we are looking for the y-coordinate over here. We'll have a squared plus b squared equal to c squared. That gives me 25 plus y squared equal to 36. Now we'll subtract the 25 over here. We have y squared equal to 11, and we'll square root both sides. And y is going to be equal to the negative square root of 11, because in quadrant 4 my y values are negative. And now I know that the sine of angle beta is negative square root of 11 divided by 5. Okay, so now I'm ready to find the cosine of alpha plus beta. Now let's go up here, and then let's take this off right here, and we'll take this off right here. So the cosine of alpha we found to be negative 12 over 13. The cosine of beta given to us, 5 over 6. The sine of alpha given to us, 5 over 13. And the sine of beta we found right here, negative square root of 11 over 5. Let's do our multiplication. Negative 12 times 5, that's going to give me negative 60. 13 times 6, that looks like it's going to give me 78. 5 times negative square root of 11, this is going to give me negative 5 square roots of 11. And then in the denominator, that should be square root of 11 over 6, shouldn't it? Sorry about that. That should be over 6 right there, because that one should be over 6 right here. The hypotenuse was 6, it wasn't 5. Sorry about that. All right, and then 13 times 6 we said was 78 here. Okay. And then if we want to write this as one fraction, we can write it as negative 60 plus 5 square roots of 11 over 78. And that is our final answer right there. Example 4, find the exact value of the cosine of the inverse sine of negative 12 over 37 plus the inverse tangent of positive 5 over 12. Okay, now this looks a little bit scary at first, but what we're doing is we're finding the cosine of the angle where the sine is negative 12 over 37 plus the angle where the tangent is 5 over 12. And we can actually do this without having to figure out what those angles are, just by drawing the triangles. But before I do, let's expand this using the cosine formula. All right, so that means I'm going to have the, oops, sorry, I don't want the cosine there, do I? Okay, so I want to have the cosine of the inverse sine of negative 12 over 37 times the cosine of the inverse tangent of 5 over 12. Change the sign, so we're going to subtract the sine of the inverse sine of negative 12 over 37 times the sine of the inverse tangent of 5 over 12. So this is what we're looking for. Remember, the cosine formula is cosine times the cosine minus the sine times the sine, and that's exactly what I have right here. So I need to find the cosine of the angle where the sine is negative 12/37. I need to find the cosine of the angle where the tangent is 5/12. I need to find the sine of the angle where the sine is negative 12/37. And I need to find the sine of the angle where the tangent is 5/12. All right, let's take a look at this. My first angle tells me that I know the angle has a sine of negative 12/37. Okay, the inverse sine has been restricted to quadrants 1 and 4. And in quadrant 1, the sine is positive. So that means this angle is going to have to go down here in quadrant 4. We have negative 12 over here, 37 on the hypotenuse. We need an x value so we can figure out what the cosine is. We have a squared plus b squared equal to c squared. We have x squared plus 144 equal to 1,369. We'll subtract that 144 to the other side, and that gives me 1,225. Now let's square root both sides. And that leaves me with 35. It has a nice square root. All right, so the cosine of that angle, and I'm just going to call it theta, is x divided by r. And the sine we knew was negative 12 divided by 37. All right, let's look at our other angle where we know the tangent is 5/12. The inverse tangent function has been restricted to quadrants 1 and 4. And in quadrant 1, the tangent is positive. Quadrant 4, the tangent is negative. So since this is a positive value, we know this triangle is going to be over here in quadrant 1. And this angle we'll just call P. The tangent is the opposite side divided by the adjacent side. So the 5 is going to go here, the 12 is going to go here, and we are missing the hypotenuse right there. So let's use the Pythagorean theorem to find that hypotenuse. We have a squared plus b squared equal to c squared. That's 144 plus 25 equals r squared. 144 plus 25 gives me 169. And when I square root both sides, the square root of 169 is 13. And we want the positive square root, remember, because our hypotenuse is always a positive number. Okay, the sine of our angle P is going to be the opposite side divided by the hypotenuse, and the cosine of our angle P is going to be the adjacent side divided by the hypotenuse. And now I have all I need right here to solve this or simplify this expression right here. This part right here is asking me, what is the cosine for the angle where I knew the sine was negative 12/37? Well, that's my angle theta here. The sine is negative 12/37, and the cosine that goes with it is 35/37. this piece right here is asking me what's the cosine for the angle where the tangent was 5/12. Well, that's over here. We knew that the tangent was 5/12, and the cosine of that angle was positive 12/13. All right, and then we're subtracting. This piece here is asking me what's the sine for the angle where the sine was negative 12/37. Well, that's just negative 12/37. And then this piece here is asking me what's the sine for the angle where we knew the tangent was 5/12. That's this side over here. The sine we found to be 5/13. Now we just do our multiplication. All right, let's see. 35 times 12. This is 420. And 37 times 13 is 481. And then 12 times 5, that's going to give me negative 60. And we just added, I multiplied 37 times 13, it gave us 481. These two negatives are going to cancel each other out, so we're going to actually add 420 plus 60 over 481, and that's going to give me 480 divided by 481. And there is our solution. Example 5, find the exact value of the tangent of 165 degrees. So once again, just like we did the problems of sine and cosine earlier, we're going to try and find two angles on the unit circle that add up to 165. And we're going to do it this way because 165 is not on my unit circle. And so if I want to find the exact value of the tangent, I'm going to need to do it this way. Now, just like before, we're going to go to the unit circle and we're going to find two angles that either add or subtract to give us 165 degrees. And again, there's a whole lot of different pairs that'll do this for us. So as long as you choose a pair that combine to give you 165, we should all come out with the same answer in the end. All right, one thing that I see is that the tangent of 165 is the same thing as the tangent of 120 plus 45. And if we expand that using the sum of our tangents formula, we'll have the tangent of 120 plus the tangent of 45 divided by 1 minus the tangent of 120 times the tangent of 45. Okay, on the unit circle, over at 120 degrees, we know the coordinates are negative a half, positive square root of 3 over 2. So the tangent for 120 is going to be negative a half, it's going to be square root of 3 over 2 divided by negative a half, which is the same thing as the square root of 3 over 2 times negative 2 over 1, and the 2's are going to cancel and leave me with the negative square root of 3. At 45, the coordinates are square root of 2 over 2 and square root of 2 over 2. There we go. So the tangent at 45 is going to be square root of 2 over 2 over square root of 2 over 2, which is the same thing as the square root of 2 over 2 times 2 over the square root of 2, and they'll cancel, and they'll cancel, so the tangent at 45 is going to be 1. All right, let's fill in our formula here. The tangent at 120 we said was negative square root of 3. The tangent at 45 we said was positive 1. Down here in the denominator, we have 1 minus. The tangent of 120 we said was negative square root of 3. And the tangent of 45 we said was positive 1. Let's clean this up a little bit. We've got negative square root of 3 plus 1 divided by 1 plus the square root of 3. Because these two negatives are going to cancel out, and the square root of 3 times 1 is going to give me the square root of 3. Alright, now we need to rationalize the denominator. This is a binomial here. It has two parts to it. And so in order to get rid of that radical down there, I'm going to have to multiply by another binomial. And I'm actually going to multiply by its conjugate. So if this is 1 plus the square root of 3, the conjugate is going to be 1 minus the square root of 3. And since this fraction here has to be equivalent to 1, we're going to multiply the numerator by 1 minus the square root of 3 as well. Once we do our FOIL multiplication here, negative square root of 3 times 1, that's negative square root of 3. Negative square root of 3 times negative square root of 3, that's going to give me a positive square root of 9. Positive 1 times positive 1 is going to give me 1. And positive 1 times negative square root of 3 is going to give me a negative square root of 3. In the denominator, 1 times 1 is 1. 1 times the negative square root of 3 is negative square root of 3. Positive square root of 3 times 1 is going to give me a positive square root of 3. And the positive square root of 3 times the negative square root of 3 is going to give me a negative square root of 9. In the denominator, I can see my square roots of 3 are going to cancel each other out. Let's add our like terms. I have a negative square root of 3 here, a negative square root of 3 here. That's going to give me negative 2 square roots of 3. The square root of 9 we know is positive 3. And 3 plus 1 is going to give me 4. In the denominator, the square root of 9 is 3. And I have 1 and a negative 3. 1 minus 3 is going to give me a negative 2. And so we can actually reduce this a little bit further because my fraction can reduce. And I'm just going to separate this so I can reduce them individually. In the first one, the square roots of 2 will cancel. That's just going to leave me with the square root of 3. And then 4 divided by negative 2 is going to give me negative 2. And so my solution is square root of 3 minus 2. Example 6, verify the identity. The cosine of 3 pi over 2 minus theta is equal to negative sine theta. Now this is not as bad as it looks here. We're going to take one side, because this is how we do identities, and we're going to try and make it look like the other one. And I would totally work on the left side here because there's more stuff over here to work with. And it's easier to take a lot and simplify it down into one thing than it is to try and take the one thing over here and blow it up or expand it so that it looks like what's going on over here. Okay, the next thing I notice is that I actually have a difference between two angles here. One of them I know and one of them I don't. That's okay. I'm going to apply the formula for the difference of cosines, and that means we're going to have the cosine of the first angle, 3 pi over 2, times the cosine of the second angle, theta, which we don't know. Change the sign, and then we're going to have the sine of the first angle, 3 pi over 2, times the sine of the second angle there, theta, and all of this we want to be equal to the negative sine of theta. Okay, now this I can simplify, the cosine of 3 pi over 2, because that's on the unit circle. In fact, on the unit circle, the cosine of 3 pi over 2 is 0. So we have 0 times the cosine of theta Again, I can simplify this one because 3 pi over 2 is on my unit circle, and the sine at 3 pi over 2 is -1. And then we have a sine theta left over here. So this is -1 times the sine of theta. And again, we want this equal to negative sine theta. Well, 0 times the cosine, that's just going to be 0. -1 times the sine is going to give me a negative sine. And so 0 minus the sine of theta is just going to give me a negative sine theta. And on the other side, we wanted it to be equal to negative sine theta. So it looks like we've proved our identity. Example 7, verify the identity, the sine of x plus y minus the sine of x minus y is equal to 2 times the cosine of x times the cosine of y. Okay, once again, I have a whole lot of stuff over here on the left-hand side and just a little bit over here. So I'm going to be working on the left-hand side. Also because I see that I have a sum of two angles, the sine of the sum, and a sine of a difference. And I have formulas for those. So what I'm going to do is I'm going to expand both of these over here on the left. The sine of x plus y is going to be the sine of x times the cosine of y plus the cosine of x times the sine of y. Now I'm going to expand the sine of x minus y. That's going to be the sine of x times the cosine of y minus the cosine of x times the cosine of y. Oops, times the sine of y. Sorry. It should be times the sine of y there. Try that again. Okay, cosine x, sine y. And we want this to be equal to 2 times the cosine of x times the sine of y. All right, let's distribute this negative right here into the parentheses. We have the sine of x times the cosine of y plus the cosine of x times the sine of y minus the sine of x times the cosine of y plus the cosine of x times the sine of y, and we want this to be equal to 2 times the cosine of x times the sine of y. Now the sign change here was because we multiplied a negative times a negative right there. All right, let's add our like terms. I've got a sine x cosine y here, a negative sine x cosine y here. Looks like they're going to cancel each other out. I have a cosine x sine y here, another cosine x sine y here. That gives me 2 of those cosine x sine y's. And we wanted that to be equal to 2 times the cosine of x times the sine of y. So it looks like we have just proven our identity. Example 8, write -4 times the sine of x plus 3 times the cosine of x in the form k times the sine of x plus a. All right, let's remember what everything is. K is going to be the square root of a squared plus b squared. And this coefficient here is going to be our a. This coefficient here is going to be our b. And then our angle alpha there is going to be the place where the cosine is a over, what is it? It's a over k and the sine is going to be b over k. All right, let's find k first. K is going to be equal to the square root of -4 squared plus 3 squared. This is the square root of 16 plus 9, which gives me the square root of 25. And then the square root of 25 is just 5. So our k is going to be 5. The cosine of the angle is going to be -4 divided by 5, and the sine of our angle is going to be +3 divided by 5. And since our cosine is negative and our sine is positive, that puts our angle in quadrant 2. And to find angle alpha, I'm going to use the cosine because the inverse cosine is restricted to be in quadrants 1 and 2. So if the cosine of alpha is equal to -4/5, that means the angle is equal to the inverse cosine of -4 divided by 5. So our angle, and we're going to have to round this. Make sure your calculator's in degrees, by the way. We're going to do second cosine, -4/5. And rounding to 1 decimal place, this is going to give me 143.1 degrees. That means that -4 times the sine of x plus 3 times the cosine of x can be written as 5 times the sine of x plus 143.1. And there is our solution.